All right, a couple of reminders. Obviously, unit exam tomorrow. Okay, so same procedure as always. Okay, for tomorrow's unit exam. Also, a reminder that your Unit 4 exam is going to be June the 12th. Okay, so that's coming right up as well. We're going to go through Unit 4 very, very quickly, including starting it today. Okay. So that'll go fast. Okay, make sure you're ready for that. And also remember that the last day to hand in any overdue assignments is Friday, June 13th at 12:20. Okay. Shortly after that, I will post the sign-up sheet for the mock final times. Okay, you will only get that if you qualify to write the mock final. That is, you are not missing any assignments. Okay, if you have any missing assignments, you will not see anything about the mock final because I won't send it to you. Yeah. Okay, so make sure you got everything in so that you can take that opportunity. You don't have to write the mock. Remember, it is optional. Okay, you absolutely don't have to write it if you don't want to. Okay, it's just a chance to raise your lowest exam mark possibly and do a little extra review for the final. Okay, that's all. All right, so talking about efficiency here. So efficiency is a big focus in society because we want to be better stewards of our resources, okay, make better use of our energy and things like that. So we have tried to make energy conversions more efficient. No energy conversion is 100% efficient. Okay, you cannot convert one form of energy to another without some loss. Okay, that is not a destruction of energy, mind you, okay, because the law of conservation of energy forbids that. Okay, it is simply a loss. And what I mean by a loss is it's converted into some form of energy that does not do useful work. Okay, efficiency is the percentage of the energy you put into a conversion that actually does what you want. Okay, so you calculate efficiency in exactly the same way you calculate what percent you got on a lab or a test or a quiz or whatever. Okay, you take what you got and you divide it by what was possible. Okay, efficiency is the same thing. You divide the useful work that got done by the amount of energy you actually had to put in to accomplish it. Okay, that's always going to wind up as a decimal. Right? So if you get that and you get 0.85, what was your efficiency? 85%. Okay, just like what you would do on your calculator, right? If it spits out 0.56, you got 56%. Okay, that's how you calculate efficiency. It's a super easy calculation. You take the work that was actually done, you divide it by the energy you had to put in, which is always a bigger number, okay, and that will give you how efficient you were. All right, so the purpose of any machine is to convert the initial energy added into the type of energy needed to do the work you want. Okay, all other types of energy produced and work done are considered wasted energy, okay, or work. They transfer away. Okay, the initial energy source is called the energy input, or EI. Okay, and the desired energy is called the useful energy output, W. Okay, the work that actually gets done. Okay, and then the work the machine is supposed to do is the useful work output. Okay, so here's what we're looking at. Like for an example, looking at gasoline-powered versus hybrid vehicles. Okay, is a hybrid vehicle more efficient? Generally, yes. Okay, generally, yes, a hybrid vehicle is more efficient. Why? A hybrid vehicle has both a gasoline-powered engine as well as a battery-powered electric motor. Okay? A regular car just has a gasoline-powered engine. Why is a hybrid vehicle more efficient? Because electric motors are more efficient. An electric motor generally converts its input energy into useful output at about 95%. Okay? Very little energy is lost in an electric motor because there aren't as many points of contact. Okay? In an electric motor, you've got all those magnets, so the two parts don't touch each other. There's way less friction in an electric motor than in a gasoline-powered engine where metal pistons are going up and down inside a metal cylinder and they're rubbing against each other the entire time. Okay? That's highly inefficient. The other reason the gasoline-powered engine is less efficient is because it's using heat or thermal energy to make mechanical energy, and that is one of the least efficient ways to make mechanical energy. Okay? So in a hybrid vehicle, you have an electric motor that assists. Now, hybrid vehicles are not always the best solution if you want to use less fuel. Okay? When is a hybrid vehicle best? When does it do its job best? In the city or on the highway? When do you suppose a car uses the most energy? When it's traveling at a constant speed or when it's accelerating? When it's accelerating, right? When you're accelerating, are you changing your kinetic energy? If you're traveling at a constant speed, that's not nearly as hard, is it? Okay? So in a gasoline-powered car, when you want to change your speed and accelerate, you use a lot more fuel. Okay? Because you make the car work harder. Okay? You put more fuel into the engine, it generates more power, it accelerates the car. For a hybrid vehicle, when you press the gas and want to accelerate, both the gasoline-powered engine and the electric motor kick in. So the electric motor assists the gasoline-powered motor, right? So that makes the gasoline-powered motor not have to work as hard, okay, and thus use less fuel. Oftentimes, you'll see hybrid vehicles, like if you have the same model of car, one hybrid, one not, the hybrid vehicle will often have a smaller gasoline engine, which would also be more efficient because it doesn't need a bigger engine because the electric motor will help. Okay? So a hybrid vehicle does its best work in stop-and-go traffic. On the highway, it basically just runs as a gasoline-powered machine. Okay? Because you're not accelerating very much. It might, kick in the electric motor on a big hill or if you went out to pass somebody, but how often is that happening? Most of the time you're just traveling along a straight level road. Okay, so if you're buying a hybrid vehicle, which is a good choice, make sure you're getting it for the right kind of use. It's more efficient in certain situations. Okay, like for example, okay, I drive a hybrid vehicle now. My wife has a plug-in hybrid vehicle. Okay, and what I've noticed with my hybrid vehicle is I actually get better gas mileage in town than I do on the highway. Because on the highway, it just runs the gasoline motor, okay, and the turbo sometimes, okay? But when I'm in the city, I'm always seeing that electric gauge kick in. It's always the electric gauge is kicking in, the electric motor is telling me we're helping out the car, and it's not working as hard, okay? I went to that vehicle from a V8 powered truck, okay? My fuel consumption is down considerably, okay? Because I'm not having to throw gas at 8 cylinders versus 4 and an electric motor. Okay? Now, are there some sacrifices? Yes. It's not as fast. That's okay. Okay? I'm old and I'm not racing anybody anymore. Okay? But it uses less fuel because it's more efficient. There's a way to make better use of the gas that goes into that car. Okay? So if we're looking at a gasoline-powered engine, this is basically how all of us get to work in the morning or get to school in the morning. Okay? The losses from the engine. So if you put, let's say, $100 worth of gas in this car, okay, $68 to $72 of that fuel doesn't move the car forward. Okay, 68 to 72% is lost as heat in the radiator, in the exhaust system, okay, combustion, pumping, friction, okay? There's all kinds of things inside the engine that take energy off, okay? You ever pull up next to a car at a stoplight and it's squealing? Have you ever heard that weird squeal some cars make? Okay, that's the water pump, okay? And it runs on a belt. So it takes power off the engine to pump coolant through the engine to keep the engine from destroying itself, okay? That takes $4 worth of your $100 in fuel, okay? And this stuff, 58 to 62%, is just heat that your car has to get rid of in order to not die. Okay, so it goes out the exhaust pipe or it goes out the radiator. If you ever stood in front of a car that's running, you can feel the heat coming out. Okay, that's the radiator pushing the heat out. Okay, so $68 to $72 of your $100 of fuel doesn't even push the car forward. Okay, then you have electrical losses. So you've got your fan inside when you turn on your air conditioner. Okay, it's going to take energy. The alternator provides the electricity. Okay, seat and steering wheel warmers, headlights, your stereo. Okay, if you're like the guy that drives through my neighborhood all the time, he plays the same song all the time. It's that guy. I don't know. Does he drive through your neighborhood too? Okay, but he's got to have like an extra alternator to power all the stereo, okay, in his car, because you can register him on a seismograph when he drives through the neighborhood. Okay, that takes extra electricity. All of that comes from the fuel. Okay, parasitic losses, so water, fuel pumps, ignition systems, okay, engine control systems, that would be pollution control. All of that stuff takes energy away. Okay, so when it comes right down to it, okay, energy to the wheels is 16 to 25%. So of the $100 in fuel you put into that car, somewhere between $16 and $25 of it is actually moving the car. The rest is wasted. Okay, so not super efficient. Okay, now you've got drivetrain losses. Okay, again, that's like friction between moving parts. Idling losses. Okay, if you stop at a stoplight and your car keeps running, are you just wasting fuel? Do most modern cars turn off automatically? They do. Okay, if you have a car built after probably 2010, it probably has an engine idle disabled. Okay, which means when you stop at a stoplight, the car turns off. When you press the gas, the car turns back on. Okay, hybrid vehicles all do that. I had to get used to that with ours. It's a little annoying. Okay, so your car's not running, and then you press the gas and it has to start and then go. Okay, but it saves a lot of fuel. You use a lot of fuel just sitting there idling. Okay, so about 16 to 25% for a typical gasoline-powered car. Now, same model of car, but now it's the hybrid. Okay, so now our engine losses go from 68 to 72 to 65 to 69. Remember, it's still a gasoline-powered engine. Okay, that's still its primary source of power. Okay, so there's still all of those. Okay, parasitic losses, okay, 4 to 6%, so that's the same. Okay, you still have a fuel pump, an oil pump, and all that kind of stuff. It's all still there because you have a gasoline-powered engine. Okay, your auxiliary electrical losses, same number. Okay, 0 to 3. Okay, drivetrain losses 3. But here's where you gain something. In a hybrid vehicle, you get this: recovered energy from something called regenerative braking. We talked about this at the beginning of the unit. It's a thermocouple, and it's embedded in the brakes. So when you apply the brakes, the heat that's generated gets turned back into electricity, which goes back into the battery. Okay? Both of our hybrid vehicles have a thing called a brake coach. It's like a game. Okay? And when you're slowing down at a stoplight, the better you slow down, the more energy gets put back into the battery, and then it gives you a score every time you stop. Okay? It's like regenerative braking, 80% energy return. That's a bad score. Okay? I like to get 100% every time. Okay? And you can, if you slow down slowly and gradually, okay, it'll feed that energy back into the battery. Okay? So you get some of that energy back. Okay? Otherwise, that energy just goes into the environment as heat, and it's lost. Okay? So you get some of that back, 5 to 9%, which now takes that energy to the wheels much higher. Okay? It starts where a combustion engine would leave off. Okay? Much more efficient. Everybody with me there? Okay? Now, again, that's if you're using it as it's intended. If you're just cruising along the highway, it's probably more like this. Okay? More like the 24. Now, what about an electric car? Anybody got a Tesla? A swastika truck? A swastika car? That's the big joke now. They call it that. Okay? So, in an electric car, okay, you have no internal combustion engine. So is an electric car more efficient? An electric car is way more efficient. Okay? Way more efficient than an internal combustion engine. Okay? So, but you still need to use energy to get to work. But you're using electricity instead. Electric motors, remember, operate at about 95% efficiency. So are you using any fuel anymore? No. But what bill in your house is going up now? Your electricity bill. Okay? But people notice right away when they shift to an electric car that the amount they spend to operate their car greatly decreases because an electric car is more efficient. Okay? Like our second vehicle is a plug-in hybrid. That means we can drive about 50 kilometers on pure electric. Okay? It can operate as an electric vehicle. Well, we did the calculations. To charge it completely costs us about $1.25, okay, in power. And then we can drive 50 kilometers on that electricity. Okay? To drive it purely gas operated costs us over $4 to drive the same amount of distance. Okay? It's way more efficient to run on the electric motor. Okay? So when we look at those, obviously you have none of those combustion losses. There's no combustion engine here to cool off. Okay? So you've got your accessory losses, you still got your fans and your lights and your stereo. Okay? Electric drive system losses, 18%. That's way better than the 68% of a combustion engine. Okay? Your auxiliary electrical, 0 to 4. Okay? But then you've got your regenerative braking again, because an electric vehicle is going to do that. It's going to send that electricity back to the battery instead of just venting it out into the environment. Okay? So you end up, okay, when you look at the recovered energy from the braking at 87 to 91% efficiency. So if you use $100 of electricity to charge your car, $87 to $91 of that actually move the car forward. Okay? As opposed to in a combustion engine, maybe $24 actually moved it forward. Okay? It's way more efficient. Now, are there downfalls to an electric vehicle? Okay? It's not all sunshine and rainbows for an electric car. They have a battery. Batteries full of toxic chemicals that are often mined in very environmentally unsound ways. Okay? So you're picking your poison. Am I putting carbon dioxide into the atmosphere, or am I putting toxic chemicals in the ground later when my battery's no good anymore? Okay? There's certainly a trade-off there. Okay? Because sometimes people say, I want to drive an electric car because I want to do my part for the environment. And certainly from an efficiency standpoint, you're doing that. But the battery's got to go somewhere when it's no good anymore and it's full of toxic chemicals. And if you're in Alberta, where do we get most of our electricity from? Over 90% burning coal. So when you plug in your Tesla, you're making the electrical plants burn more coal. So you're still using an electric car powered by fossil fuels, because that's where most of our electricity comes from. Unless you're like the people in my neighborhood who bought an electric car and then put solar panels on their house. Okay? Because a bunch of people did that. They bought an electric car, then they put solar panels on the roof, and the solar panels charged the car. Okay. You've removed your carbon footprint then. Okay? But you always have to make kind of an informed decision. Just buying an electric car does not make you the savior of the environment. Okay? There are still environmental costs to that car. Okay? All right. Making some sense about efficiency there? Okay. Another place where we try to increase efficiency. Lighting in your house. Okay? Does anybody have an old tungsten filament style Edison light bulb in their house? Probably not. Okay? We've pretty much taken them out. Okay? A tungsten filament bulb, typical in your house, would be a 60-watt bulb. That means it uses 60 joules of electricity per second. Okay? That's quite a bit, because a tungsten filament bulb makes light from heat. Okay? As soon as you flip the switch, the electricity tries to go through that tungsten filament. Tungsten is a terrible conductor, so it all turns into heat, and the filament glows and lights up your house. But it also makes a lot of heat. Okay? It actually only makes about, let's say, 4 or 5 watts worth of light while using 60 watts. Okay? So what have we replaced them with? Probably most of you in your house have LED light bulbs. You can replace a 60-watt LED light bulb with a 4-watt LED. okay? 15 times less energy, because it doesn't make any heat, okay? You could, if you reach up and grab a LED bulb, it can be on for hours. You can reach up and unscrew it. It's not even hot, okay? If you've had a tungsten filament bulb on for 2 seconds, you can't touch it, okay? It'll burn your fingers, and the bulb will break, okay? Because the oil from your fingers will burn onto the glass and break the glass. So don't touch a tungsten filament bulb unless it's been cooling for some time, okay? LED bulbs, way more efficient. Okay, that's why we put them in our houses. We use less electricity. All right, so the big thing about efficiency here, guys, is that, like I said, it's a percentage. Okay, most energy conversions involve a significant loss of energy. Okay, in Physics 20, we do a lab where we just run a cart down a ramp. Okay, and we calculate its initial energy at the top, its potential energy at the top. We measure and calculate its kinetic energy at the bottom, and very rarely do we ever have a cart at the bottom with half of the energy it started with. And it's just going down those same wooden ramps that we used. Okay, so over a distance of about 1 meter, it loses half of its mechanical energy. And that's a simple energy conversion. Okay, but that much sound and heat and whatever is produced, okay, that we lose that much of our energy, okay, just going down the ramp. Okay, so mechanical energy conversions are inherently inefficient. Okay, hey, tons. Okay, making some sense? Okay, so the formula for efficiency is super easy. Okay, it's just a percentage calculation, just like what you would on a test. Okay, you take the useful work that was done, you divide it by the total energy you put in, and then if you want, you can multiply it by 100. I just do that part in my head. All right, so if I had, let's say a machine that used, I don't know, let's say 8,000 joules worth of energy, but it only did 2,500 joules worth of useful work, okay, then the percentage would just be 2,500 divided by 8,000. Sorry guys, I forgot to start the calculator. Okay, so we just go 2,500 divided by 8,000. All right, so that's operating at about 31% efficiency. Okay, everybody with me there? All right, how do you know which one to put on the top, which one to put on the bottom? Which one will always be smaller? Okay, so if you've got two numbers, both end in joules, the smaller one is the one that goes on top. Otherwise, you'll get an efficiency of greater than 100%, which means you're breaking the first law of thermodynamics. You are creating energy. Okay, if you ever get a percentage that's greater than 100, you did it backwards. All right, so the smaller number always goes on top. Okay. Get you guys to write down this example right here, and we'll walk through it together here. Super simple calculation. So I don't care how many decimal places your percentage has, as long as you write it as a percentage. Now, I could also make you manipulate this, and I give you the percentage, and you just have to flip it around, right? It's just like using B equals D over T. It's no different than that. Yeah. Okay, so in this question here, it's talking about this crane that's lifting all this construction material, okay? It says, in the process, the crane does 2.3 times 10 to the 4 joules of work or mechanical energy input while doing 8.00 times 10 to the 3 joules of useful work or mechanical energy output. Okay, which one goes on top? The 8. Okay, that's the smaller number. And it's the useful work or the energy output. It's what was actually done. Okay, this number is the input. It's how much work had to be put in order to do the job. Obviously, nothing works at 100% efficiency. Okay, so efficiency is, okay, the energy in, okay, or sorry, the energy output, sorry, okay, divided by the energy in, and that's going to be our 8,000 joules divided by our 23,000 joules. Okay, if we punch that into our calculator, we'll get 0.34 something there. So 8,000 divided by 23,000. All right, so we get 0.347, but we have to round that last one, so 34.8% efficiency. Okay.
How do you know which number is small?
Because this is 2.3 times 10 to the 4. This is 8 times 10 to the 3. 10 to the 3 is 1,000. 10 to the 4 is 10,000.
Oh, okay.
Yeah? Okay, everybody with me on that one? Okay, it's really just calculating a percentage. Right? What I'm going to be concerned with on the exam is that you understand what efficiency is and maybe do one simple calculation. Okay, that's all. So understanding what efficiency is, how much of the input energy actually does useful work. That's what efficiency is. Okay? As long as you understand that, okay, that's what I'm concerned with in terms of understanding efficiency and then being able to calculate a percentage. Is really all I'm going to ask you to do with the math. Okay. Oh, come on. Okay, now, just so that we do one that involves a little manipulation, I want you to write down question number 1, okay? And we'll walk through that one just so you've seen one that involves a manipulation, and then I'll give you a short break and we're gonna move on to climbing. Okay, so just like any other problem-solving question, okay, so this internal combustion engine has an efficiency of 15%, okay? So the efficiency is 0.15. Okay, remember, when you calculate, you always multiply by 100. So that's the number multiplied by 100. On your calculator, it would spit out 0.15. Okay, and it's used to do 3.20 times 10 to the 4 joules of useful work. Top number or bottom number? Top number. Useful work is always the top number. Okay, and it's also always the smaller number. Okay, so that will be the energy out, okay, or the useful work. And that is going to be 32,000 joules. All right, so we're looking for the energy that went in. So remember, efficiency is energy out, okay, divided by energy in. Bigger number, smaller number. So if I want to calculate this number here, I got to get it off the bottom by multiplying both sides by it. Okay, so energy in, and then doing what with the efficiency? Dividing it over. This is like solving for t and v equals d over t. Okay, so we'll have our 32,000 divided by 0.15. When you divide by a decimal, does the number get bigger? It does. This should be a bigger number because the energy we put in would be a lot bigger at 15%. Okay, 213,333 joules would be how much we had to put in to make that happen. Okay, try not to worry too much about the math. There's not very much slash any math on this on the unit exam. Okay, if you know how to calculate a percentage, you can do an efficiency calculation, and you calculate percentages all the time. Okay. Okay, I'm gonna give you about 4 minutes here within the classroom, guys, and then we're gonna start on climate.